So we're talking about the difference between a cusp and a corner point. So there are other examples, but kind of the classic one, I think it helps to kind of have like a mental picture in your mind of a corner point. And you can see here that the slope on the right side as you come in is 1. So we would say the right-hand derivative is 1. And the slope on the left side as you come in is -1. So because it's a limit, you have a right-hand limit different than a left-hand limit. That's why the derivative doesn't exist. But it's a corner point and not a cusp because the derivative on each side is a finite number. Now, our classic example of a cusp is x to the 2/3. So when you take its derivative, you can see that, hopefully you can see, that we get this. So as you come in from the left side, you can see it visually that this slope of the tangent line is falling into a vertical tangent there. It's going to have a slope that as you approach 0, you can see it algebraically. As you come in from the left, like if you put in a really small negative, think like, negative 0.001, then a cube root of a negative is going to be negative. It'll be very small. A positive number divided by a very, very, very small negative becomes a very large negative. So the slope is going to negative infinity on the left. Does that make sense? When you come in from the right side of 0, you coming from right to left, the slopes are positive, but it's going to also fall off that cliff and go to a vertical line right there at the cusp. So you can see as you divide by a very, very small positive number, think like 0.001, you're going to get a positive divided by a very, very small positive. That's going to go to positive infinity. And that's the characteristic of a cusp, is that as you come in from either side, the slopes of the tangent lines go to different infinities. Negative infinity on one side and positive infinity on the other. Whereas a corner point, they're going to be finite numbers on both sides. So corner cusp, what else? Discontinuity. Yep. So, you got something that's got a break in it. The derivative doesn't exist at that place where it is discontinuous. So you have to be a little careful. And you saw some in your homework, I think, tonight or last night, where it was asking you with some piecewise functions. Is the function continuous? Yes or no? Is the function differentiable? Yes or no? If you answer no to the continuity question, then without doing any work, you know it is not going to be differentiable. It can't be. So don't go checking the derivative on either side. If it is continuous, they connect, you still have to look at what we call the left-hand derivative and the right-hand derivative. Are those the same or are they different? Because if they're different, you got a corner point and it's not differentiable. If the left-hand derivative and the right-hand derivative are the same, then it is differentiable. And that goes to how they connect. So is it going to be connecting with a corner point or is it going to connect in a smooth way? So if it stays differentiable, then somehow that transition from one curve to another is smooth. There's no bump in there. There's no corner point in there. And what's the fourth way you can have no derivative? Vertical tangent. And our classic example there is going to be the cube root of x. So when you graph it, you try to kind of exaggerate it. It's going to do something like that. So that's pretty exaggerated. But you can see it when you take its derivative, because if you do 1/3 x to the negative 2/3, and again, I'm going to write that in radical form, you're going to get something that looks like that, where you've got this cube root of x squared in the denominator. Now, as you approach 0 from the left, you plug in a really small negative, it gets squared, and so it's still positive. And so you get a positive over a very small positive. As you come in from the left, that slope is going to positive infinity. And as you come in from the right, you plug in a very small positive number, it's squared is still positive, cube root is still positive. So in a vertical tangent, it goes to the same infinity from both sides, either positive infinity on both sides or negative infinity on both sides. Whereas a cusp, they go to different infinities on each side. So those are the four ways that we can get the derivative to not exist. Discontinuity, corner, cusp, vertical tangent. Gotta know those. That's important, okay? And you have to know their names as well. If the derivative doesn't exist, we say the function is not differentiable at that point. And if the derivative does exist, we say the function is differentiable at that point. Okay, so that's the new vocabulary, the new words there. Questions from the homework? What would you like to see done?
You do 13.
13. Well, you predicted that one, Katie, yes. So 13, we have that you got a cable made of an insulating material, and you've got E. It's going to be a piecewise function. You have K times R for R less than or equal to some R sub 0, and K R sub 0 squared over R for R greater than R sub 0. And there's electric charges, the E, and electric field, distance R from the center of the cable. That's not terribly important for mathematicians, but I guess that gives us a context. I'm worried about knocking that over. Okay, and so we are trying to answer the question in 13. Is it continuous, differentiable, and sketch a graph? So, continuous, differentiable, and let's see if we can get a graph of this thing. So the continuity piece is, are they going to connect? And so we, like we've seen this before, you're going to plug in R sub, now it's really confusing here. You've got all these letters. So it's important to recognize that K is just a constant. We don't know what it is, but it's not changing throughout this problem. The R sub 0 is some other constant. I think it's like the radius of the cable, whatever it is there. And the R is the variable. That's the thing that's changing. So you're looking at, like if you cut this cable and you looked at it, R sub 0 is the physical distance from the center of the cable to the edge. And the R is this thing that's changing. So we're looking at the electrical charge as you work your way away from the center of this cable, which you don't really have to know to do this, but that's the idea. So to be continuous, we're going to plug in R sub 0 here. So when we do that, when we plug in R sub 0, we're going to get K R sub 0. We're going to do the same thing here. We're going to plug in R sub 0, and we're going to get K R sub 0. Is that cubed or squared?
Squared.
Squared? Okay, squared over R sub 0. And since one of these R sub 0s will cancel, we're going to get K R sub 0. So since these are the same, and we have the left-hand limit equal to the right-hand limit equal to the value of the function there, then we can say, yes, it is in fact continuous. Is that okay? Now, if we said no to this question, we would automatically know it would have to be no to the differentiable question, because it cannot be discontinuous and be differentiable. And you can fool yourself there if you start looking at left and right-hand derivatives without first considering the continuity question. So even if I didn't ask this question, you would have to answer that question before you could answer this one. Okay? So now what we want to do is we're going to take the derivative on each side. So here we're coming in from the left side, values of R that are less than R sub 0. I'm going to call that a left-hand derivative. And that's commonly accepted abbreviation. So I'm going to take the derivative. Now, when you look at all this stuff, the K and the R sub 0s are constants. We don't know what they are, but there's some number. It's the R's that are the variable. So when you differentiate constant times r, like you would a constant times x, its derivative is going to be just a constant. It's going to be k. You with me? Now, the right-hand derivative here, now, if we sort through all of the confusion with the different letters, that's a constant k times r sub 0 squared, still a constant. And for derivative purposes, I'm going to think of over r as being r to the negative 1. I haven't taken a derivative yet, but now I'm ready to. So when we differentiate that, the constant stuff just stays as it is. That's not changing. The thing we differentiate is the r to the negative 1. That's like x to the negative 1, and we're going to use the power rule. So we're bringing the exponent out in front, negative 1, times r to the subtract 1 from the exponent, it's negative 2. Does that make sense? That is a little bit daunting the first few times you see ones with all these different letters in them. We just have to be able to see through it and understand what it means. We're going to evaluate that at r sub 0. So I'm going to say at r equals r sub 0. It's some kind of calculus notation to show evaluation. So we're going to get then, now maybe first I'm going to write this as negative. I'm going to go back to the fraction notation there. So the r to the negative 2, I'm going to go back to calling over r squared. Now plug in the r sub 0, and we got negative k r sub 0 squared over r sub 0 squared. With me? So the r sub 0 squareds are going to cancel, and we're getting negative k. So what we take away is the left-hand derivative is k, the right-hand derivative is negative k. Is this differentiable? It is not. So it is continuous, but it is not differentiable. So we have both derivatives are finite numbers, but different finite numbers means it's going to be a corner point. So when we go to graph that, I don't know where r sub 0 is. Nobody does. We're going to say it's right there. And we know to the left, it's going to be a straight line. And to the right, it's going to be, what in the world is that? Well, this k r sub 0 squared over r is like k r sub 0 squared, some constant, times 1 over r. So with your finger in the air, what's the graph of 1 over x look like? Yeah, it's the thing that's in quadrant 1 and quadrant 3, but we're not really probably interested in the negative values. So it's going to look like this. So we're going to say, it's going to come down here something like this. But we're only going to pick it up at r sub 0. So the part to the left, and that's going to be a solid dot. So we're going to get something that's going to eventually approach that x-axis as an asymptote. So that's what it's looking like to the right. And to the left, I'm sorry, that was this part, yeah, that's to the right. And I guess that was an open circle initially. But here it's going to look like, well, what does y equals kx look like? It's just a line through the origin with slope k. And we said it's continuous, so our line through the origin, now that we've graphed this part, we're going to have to make it aim so that it's going to connect to this. So it's going to be something like that. Does that make sense? We thought piecewise functions were tough last year. Anything else? Yeah.
Could you please do 16?
16. Katie was giving me previews of all the questions in class here at lunch. She called those, right? 16. So now we have how behavior can be given beneath the surface under normal working function. Consider the function. We didn't do this one, Katie, did we?
Oh, we did.
Did we?
Mhm.
Oh, there is one. 0, and x squared for x greater than or equal to 0. And we're going to graph this thing, and we want to know, does it have any vertical segments or corners? Is it differentiable everywhere? Then we're going to sketch the derivative of that prime. And then we're going to look at the derivative function and ask more questions. Okay. So if we graph this thing, and this part is going to be just a horizontal line. So that's going to be this thing right there, y equals 0. And then we get a parabola, and so we know that's going to go like this. So I think we can see pretty clearly it's going to be continuous. You plug in 0 here, that's always 0 no matter what you plug in. When you plug in 0 there, it's going to be 0. The more interesting question is it differentiable? So when I ask the question, is it differentiable? So then we want to know, does the left-hand derivative equal the right-hand derivative at x equals 0? That's our question. Well, the derivative of 0 is just 0, so that is just always 0. The derivative of x squared, using our power rule, is 2x. And when we evaluate that at x equals 0, 2x is also 0. And so we get the left-hand derivative is equal to the right-hand derivative. So that means the derivative exists and it is 0. We say the function is differentiable. Well, what that's saying is we could see that this was going to be continuous because they meet. Now what we're seeing is they meet in a way that is, and this is actually a mathematical term, that is smooth. Okay, they just flow and connect there because the derivative exists all the way through that point where they come together. That is not a corner point where you come in with one slope and then from the other side come in with a different slope. So it is not a corner point, it is in fact differentiable the way that connects, which is kind of cool, kind of interesting. Okay, so now we look at the derivative. So now on the same graph, I'm going to graph the derivatives. So f prime of x is going to be, well, the derivative of 0 is 0. That's still going to be the case. The derivative of x squared is 2x for x greater than or equal to 0. So when we graph it, we're still going to get, this looks the same to the left, but now to the right, we're going to get a straight line that has slope 2. Now, is it continuous? Well, yes, because on the left, this is 0. On the right, when you plug in 0, it is 0. So it is continuous. It's a yes. Is it differentiable? Well, now, when you look at its derivative, which we would call the derivative of the derivative is f double prime of x, the derivative of 0 is still 0, but the derivative of 2x is 2. So now the left-hand derivative is 0, but the right-hand derivative at 0 or anywhere is 2. And since the left-hand derivative is not equal to the right-hand derivative, this is not differentiable. That is, in fact, a corner point. So the way that the derivatives connect is not smooth like the way the original functions connected. Does that kind of make sense? These are really deep questions here. I mean, this is where you're really getting into some pretty serious math about understanding what we mean by continuity and differentiability. And they say, is the second derivative differentiable? So the second derivative, so now if we look at f double prime of x, well, the derivative of 0 is still 0, but now the derivative of 2x is going to be 2, always. So it is going to look like this. And so now, is it continuous? No. And so as soon as you say it is not continuous, then the answer to the question, is it differentiable, is no, it can't be. So it's not continuous, it can't be differentiable. All right, good questions. Anything else? Oh boy, never enough time. Okay, so I want to probably do more than I can do in one class period. We'll see. So I want to talk about more versions of the derivative. So let's kind of see where we are. And you're going to need to be able to evaluate a derivative using the definition. So that's a must-have. But you're also going to have to recognize when you may see these, like in multiple choice questions on the AP exam, the different versions of the derivative. So recognition as well as can you actually do one are both going to be important here. So we know that, the derivative at a point, the derivative of x, the point A, comma, f of a, is f prime of a is equal to, and so we have a couple of versions of this. One that we're probably most familiar with is that f prime of a is, I said that already, the limit, sorry, as h goes to 0 of f of a plus h minus f of a all over h. Now there's another version of that as well. So a second version of this is, let's say a second version is that f prime of a is the limit as x approaches a of f of x minus f of a all over x minus a. So there's another way of getting to the derivative. Now, some books write, usually older, more traditional college textbooks, will write this first version, instead of using h's, they will use delta x's. So just, I put it here so that you don't get confused if you should see this. So I'm going to say, alternatively, we could say that f prime of a is the limit as delta x goes to 0. So instead of using the h, we'll use the symbol delta x. And that will be f of x plus delta x, a plus delta x minus f of a all over delta x. So that is the same kind of thing. Okay, so that's old news. We've seen that, we've talked about it. I want to talk about what's known as the symmetric difference quotient a little bit here. So related to this, so I'm going to come up here. The symmetric difference quotient. So it's the same idea that we've been doing, but it tries to maybe speed the process up. So what we know is that for this limit to exist, that the right-hand limit must equal the left-hand limit. Well, the symmetric difference quotient tries to kind of split the difference. And it goes, the limit as h goes to 0 of f of a plus h minus f of a minus h all over 2h. So visually what we have is, here is our function y equals f of x. And this is our point A, and we're interested in finding the derivative, which is the slope of the tangent line at that point. So our previous version imagines that you go h away and you push that h towards 0. So you come in this direction. And then you come over here and you choose h to be a negative number, and you push that in there. And so you say, if the right-hand limit is equal to the left-hand limit, then the limit exists, and that's what we're going to call the derivative of the slope of the tangent line. So what we're trying to do with this symmetric difference quotient is do this at the same time. So we're starting with a point that's h to the left, and another point that's h to the right. And so what this represents without the limit, what this symmetric difference quotient represents without the limit, is the slope of the line on either side of that point. H on either side of the place where we're trying to find the slope of the tangent line. Does that kind of make sense? And so if we took that limit, we would just be pushing this towards there and saying, does that limit exist? And so if it did, the claim is that would be f prime of A. Well, it comes with a little bit of trouble here. Because one problem here is it never tries to evaluate this at the point where we're trying to find the derivative. So what if, hypothetically, this thing had a hole in the graph there? This would never encounter that. And so you could do this limit and get an answer when in fact the derivative doesn't exist. And so that is the danger. Now here's how this applies to us. Our calculator will find a numerical derivative. And I'm going to show you how to do this two different ways here. The way it does it is it uses this symmetric difference quotient. It doesn't do the limit. Our calculators can't do the limit. There are calculators out there that can, but they're not legal on the AP exam, so you can't use them, and we don't even really talk about them. But what our calculator is going to do, when we say, what is, say, f prime of 5, what it's going to do is it's just going to, like you were doing in the very beginning of this chapter, it's going to plug in a very small number for h. And I think it's like 1/1000th. It's either 1/1000th or 1/10,000. So it will approximate this derivative by taking f of 5, I think it's 0.001, minus f of, it'll subtract that, so 4.999 all over 0.002. That's what it's going to do. And it's going to do that computation and just spit that answer out and say, that's it. That's the slope of the tangent line at 5. The remarkable thing is that that will be accurate to as much accuracy as we need, at least to 3 decimal places, almost all the time. The bad news is this will give you wrong answers sometimes. And that's what we want to explore today. So, for those of you who have come to believe the calculator is the source of all truth, today is a bad day. Because you will find out that, in fact, if you aren't careful and you ask it the wrong question, it'll lie to you. It'll give you the wrong answer. And so you have to know that, understand why, what the calculator is doing and why that isn't going to work, and not ask it to do something that it can't do. Okay, just know that. All right? That's our goal. Okay, so visually, what we see is this symmetric difference quotient versus what we're doing. Okay, so let me show you how to do this anyway. So bust out your calculator and let's find the numerical derivative a couple different ways. There's 2 different ways we can do this on your calculator. So we'll do something easy. We'll say f of x equals x squared. We're going to find f prime of, say, 3. So we know that f prime of x. What is f prime of x if f of x is x squared? 2x. So f prime of 3 is going to be 2 times 3. So we should be getting 6. Okay? All right. See if I can do this. I'm going to hook up my calculator. And we'll see if anybody's got a really old calculator, or TI-83, which will do it differently than the new, modern, cool ones. You really want to go this way. Plug in. There we go. So let's put in y equals x squared into our graphing menu while I get mine hooked up. All kinds of junk in there. See if I can bring up my calculator. Can you look at the clock? Because doesn't it go really slow when you're watching the clock? Just keep your eye on the clock for me for a bit. I'm just joking. No, there we go. Okay. And on my next challenge, see if I can put the camera on my calculator. I'm getting seasick when they're watching this video. Okay, so I think we got it. So, first thing we're going to do is what's called NDeriv. So go to the map button, and you should look at this screen. Hidden out of sight, option number 8, is our NDeriv, the numerical derivative option. Hit enter. Oh my God, hold on there. Oh, I had to get out of the graphing menu first. Let me go back and I put x squared in there. Let me go second mode, clear that off. I'll try it again. So here's math 8. There's our derivative. Does anybody have a screen that does not look like this? Yours looks like NDeriv, like this, and it's got a parentheses. Okay, we'll do it. You got to do a little bit different entry here. You just have an older or cheaper model. This is what happens when you get the one on sale. So we're going to go derivative always with respect to x. So hit the x comma t comma theta button. Not you yet, thing. Then you're going to plug in the function. So we could type in x squared, that would be fine. Or we already have it in y1, so I can go variables, right arrow, enter, enter, and it's typing in the y1. Did I lose you already, Ainsley?
Yeah.
No, kiddo, you haven't lost your wisdom yet. And then we're going to right arrow to here, and we're going to evaluate this at 3. So we're going to hit 3 and hit enter, and magically there's what it gets. Okay? Now what you have to do is you're going to put your function in here. So it's looking for function, always x, and then whatever the number is you want to evaluate that at. So you're going to go y1 or x squared either way, comma x, and then we're going to plug in 3. And when you hit enter, you should also get the 6. Does that work? Okay? Question. Okay, now there's a second way you can do this. Now, the second way is interesting, but when you do this on an AP exam, you will be expected to be able to do this on an AP exam. Use the NDeriv feature. I don't really know why, but there's the algorithm that it uses, you get better accuracy off the NDeriv feature than you do off of the graphing one that I'm going to show you next. So don't use that on something where the accuracy matters. So let's graph this. I'm going to go zoom, 6, 10 by 10 window. Here's our parabola. Now there's a second way to get the derivative off of the graph. So we're going to go second trace to where it says calculate. Arrow down to option 6 where it says dy dx. Hit enter. And it's waiting for an x value. In fact, it puts the cursor at 0, so it's telling you the derivative at 0, 0. But if you type in 3, enter, and it's going to tell you the derivative is 6. Does that make sense? Okay. Now, here is what I'm going to do. Well, I'm going to pause this for a moment and hand out a worksheet that I should have handed out earlier. I think I can do this. All right, they're back with us. So we are looking at this one, sort of. You want to look away. If you're on the video, I'm going to go back to the board. So we are looking at this Explore Derivatives worksheet, which is available on Canvas. So what we want to do first is to provide a geometric interpretation of that formula. F star asterisk of x is equal to x plus h minus f of x over h. So what I'm looking for there is draw a graph of a function and see if you can show what that represents. Now before you get too carried away, look at number 2 right below it, which is the, and I think if I gave you the right versions, let's say contrast that with number 1. Good, that's what I wanted it to say. Now, what's the difference between number 1 and number 2? When you look at those formulas, where number 2 is written as f prime of x, is the limit as h goes to 0 of f of x plus h minus f of x over h. What should we see in number 1? What should we see in number 2? How are those going to be different? Tough question, huh?
Number 2 has a limit.
Ah, yes! Number 2 has a limit as h goes to 0. Ah, what difference does that make? Good question. What difference does that make?
Doesn't one give you a formula and the other
Okay, what formula? Okay. Yeah, what's a geometric representation? So you're going to show a graph. We want to see a graph. Here's our f of x. Our classic y equals f of x function. Here's our point x. Right there. Here is h, a little bit away from, that's actually x plus h, a little bit away from x. Hit number 1. Number 1 gets to be in orange. What geometric representation are we seeing in number 1? F star x equals no limit as h goes to 0, f of x plus h minus f of x all over h. What is that? Average rate of change. Yes. Geometrically, what does it mean? Slope of what? Yes. Of the secant line. Excellent. Average rate of change, which is the slope of that secant line. Brilliant. Okay? That's number 1. Number 2 is going to be in purple. We put in that little limit as h goes to 0 thing. How does that change things? It's the instantaneous rate of change. Geometrically, what does that mean? The slope of the tangent line. Yes. That's our slope for the purple one. Okay? Now, number 3, contrast that with what does this mean? Now, maybe should have even left off the limit as h goes to 0. What are we seeing with the f of x plus h minus f of x minus f of x plus h minus f of x minus h all over 2h? Symmetric difference quotient. Check your notes for that one. Here's x minus h. There's f of x minus h. Here's f of x plus h. We're finding the slope of that line in between those 2 points on either side of x comma f of x. That's the geometric interpretation. And then the third one, we're still taking a limit. So it would still end up being that slope of the tangent line. Okay. Now, here's what I wanted to get to and try to get you started on this, because you probably aren't going to be able to finish this, so this will become part of your homework. But I want to get you an efficient way of doing this. So you have number 4, you have A, B, C, D, E, F. You have the alphabet for number 4. And we're going to enter those into our calculator, and we're going to use the n-deriv feature to evaluate the derivative at each of those points. So to do that efficiently, what we're going to do is enter, I think we can do it like 3 or 4 of these things here. So you can do this with me, and let's first, I'm going to try to turn the camera over, so still hold on here. This is not gripping the way I want it to. Should turn it first and then re-grip. Okay, so on the calculator, let's go for y1. So we're going to go y1, clear, I didn't want to do that. Clear that old stuff out. So we're going to put in x squared minus 3x plus 2. X squared minus 3x plus 2. Drop down to the second one. Now the second one, we're going to have that same function, so I'm not going to retype it in again. We'll just use y1 again, just at a different point. Then the part C, we want the absolute value of that. Okay, you with me here now? So we're going to go absolute value, which is math, right arrow to numerical, and that first option is absolute value. Hit enter. Now inside there, we're going to put y1. So I'm going to go variables, right arrow, enter, enter. It's going to take the absolute value of what we put into y1. You with me? Okay? Drop down. D now is a whole different one. So x divided by, we need parentheses, and then x squared minus x. X squared minus x in parentheses. Okay? That will also work for E. You're just going to evaluate it at a different point. F is going to be x minus 3 to the 2/3. So parentheses, x minus 3, parentheses, raised to the 2 divided by 3 power. And Zane, your 2/3 is going to need parentheses. So parentheses 2 divided by 3 and parentheses. Okay, now, what we can do here on the end derivative is easy enough. So you're going to just go to the home screen, so second mode, and you can go to math, 8, and we can do the derivative with respect to x. We can go variables, right arrow, enter, enter, y1, at, and we'll plug in -3, enter, and you'll write that down. Now you'll go all the way through end derivative, and that's fine, and write all those down each time. Okay? Then you're going to go back in number 5 and do these same functions, but off the graphing menu and using your dy dx. Now, when you go back to y equals, right now all of these are highlighted. If you graph now, it's going to put all 4 of those graphs on there at once. It's going to look like a map of New York City. So we want to just graph one at a time. So what you can do is go left arrow, drop down, and hit enter to unhighlight the ones that we don't want to graph yet. So then when you graph it, it'll only graph the highlighted one, then do your dy dx, and then get that result. Does that make sense?
Wait, how did you do that? How did you make it unhighlighted?
So you left arrow onto the equal sign, and when you hit enter, it unhighlights it. And so then once you do the first one, and you have 2 different points on the first one, then once you want to move on to the y2, you will hit enter to unhighlight the first one, hit enter again to re-highlight the second one. Now what you're going to find is, surprisingly enough, they don't agree. I mean, they do most of the time, but there's going to be one where you get a different answer from the dy dx than you do from the end derivative. What's even more disconcerting, when you get to the second page, it's going to ask you to find the derivative of this function at that point using one of our definitions. You should find that there is, in fact, a corner point at that value of x. So your true correct answer would be the derivative doesn't exist at all. And yet, you will see that both the end derivative and the dy dx gave you an answer. And so then it's going to ask you to look at those functions and those points where you're finding the derivative carefully. You're going to see that most of those come from either a corner point or a cusp or might even be a vertical asymptote, and yet your calculator is giving you answers. And the reason is because of how it does the derivative, that symmetric difference quotient with 1/1000th on either side. And so what you need to know is don't ask, you're going to have to recognize when the derivative doesn't exist. We'll talk more about that next time. And not use your calculator to find the derivative at a point where it doesn't exist. Because the calculator will go on its merry way and give you an incorrect answer. Try to finish this sheet and the homework. There is a video on there that walks you through this whole sheet. So you should probably, maybe do that with the video as you do it, so you don't take a wrong turn. Because you can check your answers, and you can also on that.
Gia Reinders, will you
get some
come
help.
to the counseling office?
Thank you
Gia
for your patience.
Reinders?